Hello everyone. Sorry, I'm still traveling, and I have to had Professor Shuti to cover two lectures for me last week. At least this week, the last two lectures, I have to cover it myself by video. So hopefully you get good experience out of it. Um, so uh, so what I want to remind you first about this semester is that the first thing is the final exam date is on Tuesdays, December 12th and 12:30 to 2:30. And also, please remember to submit your survey, course evaluation surveys, and send me emails to get you extra credit. Okay, and in these lectures, we will continue from where we stopped, as covered by Dr. Shuti. Basically, so we almost finished the from the top bottom layers. We finished the application layer, transport layer, network layer, and data link layer. So in this lecture, first thing we're gonna do is we try to make a synthesis by using an example to put all the things we have studied together and show that all the protocols we studied, all the technologies we know. Okay, sorry, add a little bit of code. So, and the goals is we try to review what we have studied, all the protocol involved, and the scenarios we are using is that it's very simple. You bring a laptop, you connect it to the campus network, and you open web page google.com and you do a search. Okay. Excuse me. So the first step is very simple. So this is the basic scenario. You have school network right here, okay, and you have DNS server, which usually is provided by ISP, Internet Service Provider, and then the destination web service by Google, the data centers usually. So the first thing is you bring your laptop and connect to the campus network. Okay, so the first thing is you connect it, and you open a web browser. And your eventual goals is to get the Google web page displayed on your machines, which should be get from the remote server. Okay. But before that, the first things that happens is you have to kind of using DHCP to get an IP address when you move and connect to the campus network. Right. So the first thing is DHCP. The DHCP is encapsulated in UDP and then in Ethernet. Okay. Supposedly we are using wide Ethernet connections. And then you send out a broadcast saying you want to get an IP address, and the DHCP service will respond to you. Okay. So in the middle there's a switch learning process to make sure in the same net they know each other and they are connected. Okay, so eventually you will get the IP address and you know the DNS address, DNS services address, and the IP addresses of the first router. All right, that's all the things you can get out of DHCP. So the next thing is you now you get an IP address and you want to access a web page. Apparently, you need to send out HTTP request, right? But before that, you need a DNS to know the IP address of Google.com. Okay. So you need to send out a DNS query. But before that, you have to go through your local Ethernet first. So you have to know the IP address of your router you are connecting to. Right? So that again is achieved by ARP. Okay, so the router will reply and let you know the MAC address of the routing, the router's interfaces. So you send it out. You send the DNS request out, and it will go through in the domain routing. Okay, using IP or SPF routing protocols, and eventually arrived at the DNS server. The DNS server will reply and let you know the IP addresses of the Google server. Okay, and then eventually you are able to establish a TCP connections to carry your HTTP datagram. But before that, you also needed to make sure that an active TCP session is established for you, right? End-to-end TCP session. So that's when you needed to initiate the three-way handshake and establish a TCP socket. All right. So this three-way handshake is something you are very familiar with. Okay, you go back and forth and then get the TCP session established. Then all the HTTP datagram you have can be sent over the active TCP sessions you just established. So you send out HTTP request over the socket, and the IP datagrams will go through the inter-domain routing and arrive at the Google data center, and the data center will reply. The web server of the Google data centers will reply and send you the HTTP message, and it will eventually will be sent back to you and displayed on your web browser, on your laptop, and eventually you gotta see the web pages you request. So you can see it's very complex. There are so many protocol technologies involved. Okay, so this is a very simple example showcase the steps. Make sure you understand the detailed steps. So, for example, if I give you some other example, some other scenarios, and ask you to illustrate all the involved protocols and the steps, so you should be able to describe them in detail and justify them. Okay. So after this summary, after this simple examples, we summarize the whole chapter 5. So that which means the key part of this lecture, this class is concluded. Okay, but we are not gonna put an end to everything. So in addition, in this lecture and the next lecture, we are gonna study a little bit more. So what we are gonna study is wireless and mobility. So which is also very important part of the current and the future internet and computer network. Okay, so that's something we are going to cover in chapter 6. So the wireless and the mobile network part, and the reason we want to study more is because right now the numbers of wireless phone subscriber and wireless stations now already exceed the numbers of wired phone subscribers, almost 5 to 1. So everybody got a smartphone now. So it makes it more important for us to study how the wireless network work, okay, and how they are connected. And mobility is another important topic that connected to wireless. Okay, although they are not the same idea. I mean, wireless are not equal to mobility. Mobility is not equal to wireless, but they are somehow related, closely related. We will discuss more about them. So in the remaining lectures, we will try to cover the fundamental things in wireless and mobility. Okay. So in wireless, there are some fundamental elements in the wireless infrastructure. So as a matter of fact, wireless usually happens at the last hop. Okay, last hop which means, for example, from your smartphone or from your laptop to the router, the wireless router. Okay, but beyond that, they are almost wide network, which means that wireless network is always the last hop, like it is shown in this picture. Okay, the fundamental elements of the wireless network involve at base stations or multiple base stations. It's like cell tower. It's like the wireless AP in L21 access point. Okay, they are fundamental things, and it's also involved a lot of wireless hosts. They can be laptop, and they can be smartphone, on which they run all kinds of applications. They can be stationary, they can be mobile, and go to anywhere. Okay, and the third important element is wireless link. Okay, the link is kind of radio link. They are very typical links that connect mobile devices with the base station. Sometimes it's also used in backbone link, for example, for peer-to-peer connections. And for wireless links, because it's open access, which means they by competitions, and you need to compete with the other devices and mobile stations to get access. They have to show access to each other, so they need MAC protocols to make it happen, which we already discussed some. Okay. So this graph, actually, in this slide, we try to put some very typical wireless technologies, and categorize them based on the x-axis, which is the range of the signal. So from left to right, this is from small range to long range. Y-axis is the data rate. So the higher it is the faster the speed is. Okay, so basically you can see these are the mobile wireless communication technology, like 2G, 3G, 4G, in-house 3G, something like that. And it's kind of now it's even beyond that, it's 5G. So for this wireless mobile telecommunication network, they usually have long range, right? Long range. But for Wi-Fi, usually it has limited range, like indoor, like 10 to 30 meters. So you can see 11N, 11A, 11B, they are all kind of sub protocols of Wi-Fi. Okay, so 11N has the highest speed comparing with H, and B. L2.15 is body area network, low range, low power, the limited data speed. Okay, so there are a lot of more, but this picture shows some very typical ones. You can see how different they are. So in the middle, there are some L2.11A and G, which is used for point-to-point connections, long range P2P Wi-Fi. Okay, it can be used for backbone connections. So for a wireless network, there are two very typical working mode. The first working mode is called infrastructure mode. Infrastructure mode means that the base stations are connected. All the mobile stations are connected to the base station. Okay. And if the mobile device is connected to these APs or cell towers, if they move out of the one range and to the range of the other cell tower or access point, then the handoff should be taken care of by the base station. So this network handoff is facilitated by the infrastructure like the base station. Okay. There's also a mode in which all the nodes are equal. There's no base stations to work for them. They are all talking to each other directly. Okay, which is quite different from the infrastructure mode. For instruction mode, if you want to talk to another host in the same ranges, you have to go through these base stations or access point first. All right, but for ad hoc mode, these guys can talk to each other directly. They organize them with each organized network directory. They can transmit to other nodes within its own link coverage. They cannot see too far away. They have to handle the route by themselves. Okay. So if we summarize the infrastructure mode and no infrastructure mode or ad hoc modes into these tables based on if they are using single hop or multiple hop for routing, we can get this table. So if it's the infrastructure mode, like involve access point or base station. If it's a single hop, then it's very typical Wi-Fi or cellular network, right? Only one single hop. There's no relaying between different mobile stations. If it's a multiple hop and it also provide AP, then it's a mesh network. So mesh network involves relaying through several wireless nodes to connect it to the large internet, and it does have an AP or base station for mesh network. Okay. So if it is no infrastructure mode, then if it is again a single hop, then it's a very typical example is a Bluetooth network. So it's like point-to-point direct connection, no base station, device talk to devices within one hop directly. If it's a multiple hop, then it's a very typical mobile ad hoc network or vehicle ad hoc network, which involves multiple nodes, multiple hop, and they kind of still has no infrastructure or access point. Okay, so that's the summaries and differentiate all kinds of state-of-art network technologies. Okay, so after the introductions, we want to discuss a little bit more about the wireless itself, specifically the wireless link, and what the wireless link means in terms of different things. So usually the biggest difference between wireless link and the wired link is that in wired link it is kind of voltage is constant, right? But in radio, it means that radio signals can go down or decrease significantly if you this is propagated further, okay, which also called a path loss. Which means the further away you are from the base station, the more difficult you can get the signal strength, right? Which is quite different from the wire link, right? And in the meantime, there are also interferences with other sources. For example, if you are using Wi-Fi, multiple Wi-Fi signals may coexist in a single place. They may have using the same frequency band. Okay, and this can cause interference. And also, for wireless, it's very common that multipath propagation is existent. For example, when you transmit a signal, it can arrive directly, or it can be reflected. It can be going from different directions, and right. So basically, you're getting multiple copies of the same signal. You need to make sense out of this combined signal. Actually, this behavior or this effect occurs. This all makes wireless connections much difficult. Okay. So a very important concept in wireless link is called signal noise ratio, or SNR. So signal noise ratio is like the strength of the signals divided by the noise level. It's a metric used to describe how good the channel is. So apparently, the larger SNR is, the better signal it is in the channel, right? We always want better SNR or larger SNR for good wireless communications. And also there is a trade-off between signal noise ratio and bit error rate, BER. So these diagrams show exactly the relationship between SNR and BC. Okay, these three lines actually, the blue line, red dotted, and green dotted lines. Each line actually sees different modulation technologies. Okay, so if you are using one specific modulations or sending data speed, if you, for example, if you are increasing your signal noise ratio, you didn't change your modulation technologies, then you can see you go from left to right. The signal noise ratio improve, then the bit error rate will decrease significantly. That's a good thing, right? But if this signal noise ratio is fixed, then it means that if you are modulating with fast speed like QAM, then you will get worse bit error rate, which means more errors, right? But if you send with BPSK, which is lower rate, then you are able to get some much lower bit error rate. Okay. So usually, what it means that if you are having some kind of bit error, if you're sending with some, if you're sending some signal out, it's depend on the signal noise ratio you have. You should choose your modulation scheme carefully to control the bit error rate, to meet the requirement of the bit error rate. Okay, you have to make a wise decision. The other issues is that, for example, if you have a poor signal noise ratio, okay, so which means it's left hand side, right? It means that if you choose if you're sending very fast speed, the error rate will be very, very big, right? So it's kind of very straightforward. When you got bad signal or low signal noise ratio, try to send conservatively, right? Send in a low rate. But if you have good quality, good signals, you can try to send faster, which totally makes sense, right? And the other cases you have to consider is that in mobility case. So in mobility cases, as you know that when we have mobile devices, we are keep moving from one place to another, which means that sometimes we can be close to the cell tower, sometimes we can be far away from cell tower, which means our signal noise ratio is kind of always change, right? The signal noise ratio is always change, which means that if we are using some fixed modulation technologies, it means that the bit error rates can also change, right? When signal is good, it's a lower error rate. When signal is bad, it's a higher error rate. Then you have to make a wise decision. So, for example, if you don't want the bit error rate to be too high, and when the signal goes bad, you have to make some compromise. So, for example, if the signal noise ratio goes down, the bit error rate increase, then you need to do channel. You needed to do adaptive modulation, which means you needed to change to another modulation technologies with lower rate, right? To control the bit rate, error rate to some ranges you set, right? So this technology is very frequently used in wireless 3G, 4G network. So when you move your smartphone, bit error rate, the signal noise ratio, is changing all the time, and you needed to adapt these changes by changing modulation technology to control the bit error rate, right? So this graph tells you everything. And also, the wireless network, the other characteristic is I mentioned to you is the hidden node problem, right? Last time we mentioned hidden node problem and exposed node problem. The hidden node problem is because when A and C want to send something to B, they do not know each other's existence, right? So they just make their decision based on their own belief and send to B directly. Simultaneously, then B cannot accept because two people are sending to them in the same time, right? Escalation. So the hidden node problems can be caused by two reasons. First reason is obstacle. For example, there's some blockage between A and C. They cannot see each other, okay? Or they can be caused by distance. So, for example, the signal is fading because A and C is too far away. So the signal A, it can arrive B know it, but for C is too far away, it cannot see that A is sending, right? Similarly, the cases for the signal sent out by C, when it arrives at A, it's very weak and A cannot see it. So both of these two cases may cause the hidden node problem. Make sense? So, in wireless, we want to discuss a very important technology, which is called code division multiple access, or CDMA. We briefly mentioned the other two channel partitioning technologies, which are called TDMA and FDMA, right? Time division multiple access, or frequency division multiple access. So for channel partitioning protocol, the idea is we want to divide the channel resources and share them, distribute them among different mobile stations so they can get their fair share, right? So on top of TDMA and FDMA, there is also one important technology which is called CDMA. So from this graph, we can see the difference between FDMA, TDMA, and CDMA. So in CDMA, the difference is that we are not dividing the channel accesses by frequency or by time slot. Instead, we divide channel access by chipping sequence. So essentially, which means that each host, each users can use all the frequency and all the time. They are not messing up with each other. So you may be wondering how. It's kind of like a magic. So the idea is we introduce some kind of code or chipping sequence. Use this sequence to encode their original message to be sent out. Okay, so they can differentiate with each other by designing these chipping sequences to be orthogonal with each other, so that they involve minimal interferences and they can coexist with each other and can be extracted out of the channels when they want. Okay, so the benefit is very clear, because when we use TDMA, FDMA, users are only allowed to use that specific frequency or time slot. But in CDMA, you can use all the time, all frequency. But you just need to figure out some technologies to differentiate their signal from each other. They need to be isolated, right? Identified with each other. So this, the key technologies is called CDMA by using chipping sequence, okay, designed then smartly, and assign these chipping sequences to different users, so they can use this chipping sequence to separate from one another. Okay, so it's a very useful technologies. So there are two types of CDMA. So the first one is called direct sequence spread spectrum CDMA. So the idea is the top is the original data message we want to send out. Supposedly we are sending out 1 bit 0 and 1 bit 1. So the direct sequence CDMA, what it does is that instead of sending out just one bit, this waveforms, for each of the bits we use many bits to represent 1 bit original data bit you are sending out. For example, for 0, 1 bit of 0 messages you send out, in this case 10 bits. Okay, this sequence is called chipping sequence for you. Okay, is assigned to a specific user. So if you are sending 1, then they are all opposite. Whatever you send out, 0, 1, 1, 1, 0. So every bit is opposite. Okay. So whenever you send a 0, you send this bit stream. Whenever you send a 1, you send this bit stream after the encoding. So you may be wondering why we want to do this. So apparently it's very inefficient, because originally you just need to send 1 bit, but instead you send 10 bits. It's more costly, right? So this the ratio, for example, for each of the bits you originally want to send out, you send 10 times of that, then this is called the spreading factors. Okay, so in this case, the spreading factor is like 10. For each bit, you send 10 bits for it. So there are reasons why we do this. But the first concept is the spreading factors. The ratio between the original data bit, encoded data bit length, and the original data bit. So in commercial applications, spreading factors of 10 to 100 is very common. Okay. for militaries, if you are willing to pay the prices, you can do like 10,000 spreading factors, which means for each of the bit you send out 10,000 bits to represent that data bit. Kind of a lot of redundant information. So you may be wondering why we need this. So there are a couple of reasons we will be discussing, but the direct reasons is the most straightforward reasons in military. If you incorporate this redundancy, then it will be very beneficial. Because even 1 or 2 bits is correct, you can still get the information out. But in original data transmission, if one is corrupted, then you lost everything. Right? So by using this, you are guaranteeing, you are making the transmission more reliable. Right? So essentially, by using direct sequence spread spectrum CDMA, you are sending more data rate for some information, right? And you are using high bandwidth. In this case, the bandwidth you are using is 10 times of the original data bandwidth. And you have to design the code to make sure that correlations between the code is minimal, and best to be orthogonal, so that they involve very small inferences. Okay. So another reasons why we need spread spectrums is we can see these direct sequence spectrums in the frequency domain. So if we in time domain, if we want to send out this 1 bit in time domain, then in frequency domain, for this signal, what you can see is the shape of this green one. It's like a pulse with some tail. Alright? So which means that if you send the raw data, raw waveform directly, it can be very easily detected because of this pulse peak, and pretend that this is a noise. Okay? So in military, you definitely do not want to do this, because whatever information you send out can be very easily detected. We want it to be undetected, right? So that's the benefit of this spread spectrum. So if you using tube sequence like this, 10 bits of the string, 10 bits of the data to represent the 1 bit you send out, then pretty much the frequency domain, what you will see is the peak of the pulse will be much fatter. And is with low strength. So you pretty much can see that the signal waveform in frequency domain is almost it's buried in the noise. That's a good thing, because it's very secure. The spectrum is like spread among wide frequency, and is resistance to the noise and the interferences, and preventing detection because you are below the noise level. The enemy cannot detect that you are sending out data, because they cannot differentiate from the signals and the noise. Only you can do that, right? So that's a very good qualities and desirable qualities. So we want to use this simple example to discuss the encoding and decodings of CDMA. So the top part is the sender side. The bottom part is the receiver side. Okay. First things we want to study the encoding. The data bit, whatever data bit we have, we want to see how to use CDMA to encode it. And then how the receiver side just can extract the useful information out of the noise. Okay? So what happens if we have two data slots? Suppose we are sending two original data bits out. So supposedly the slot 0 we're sending is 1 bit, okay, positive 1. And for the slot 1 we are sending out -1. So you may be wondering why we don't send it out with 0. Instead we use -1 right here. So the reasons is that if we are sending zeros, then we cannot tell the differences between you are sending nothing or you are truly sending out some waveform, right? So we use -1 to represent the 0 signal, okay? So it can differentiate from itself from sending nothing, right? If you are sending nothing, it's 0. But if you see -1, it means it's not 0. It's not nothing, but you are sending some 0 message, right? So that's the deal. So you have a -1, you have 1s in 2 slots, right? You want to send out, and we select the chipping sequence for this sender. So suppose that this is the sender, which means that you are assigned to some chipping sequence. In this case, the chipping sequence is 1 1 1 -1 1 -1 -1 -1. This is 8 bit. So the spreading factor is 8, right? To send out 1 bit of the original data, you're sending out 8 bit. So the spreading factor is 8. Right? So this spreading factor, this chipping sequence is only for you. It's allocated for you. So you are using it for encoding, and the receiver use it for decoding. That's the kind of key or secret you share with the sender and receiver. Okay? So for encoding, what happens is when you send out to -1 bit, so what you do is you multiply them bit by bit. So for this, for example, -1, this is going to -1, right? So you do this bit by bit. So and bit by bit, okay, and you put them together. After the multiplication for each of this time slot, you get the product of these 2 bits. So you got this sent out to the channel, right? So this 8 bit is for slot 1s. This is for slot 0. This is for -1. This is for 1. Okay. So what happens is you send this out to the channel, and the receiver side that has the same chipping sequence, they needed to use this chipping sequence to read the information, to extract the original information, which is -1 and 1. That's our ultimate goal, right? So what happens is after you got this signal out of the channel, you receive them, and you will use your own chipping sequence to process it. So this is a copy of the data you got out of the channel, right? And this is the chipping sequences for slot 1 and slot 0. So they are the same as the sender side, right? So next step, what you do to extract the information is for each of the slots, you multiply them again, bit by bit again, and you add them together. Add these 8 product, okay, together, and the sum of these 8 product is divided by m, which is spreading factor. In this case, is 8. Right? You do this for each of the slot. You do this for this slot. You do this for this slot, and you will be able to recover. You will be able to get a digit for each of the slot. So apparently, in this case, you get -1. In this slot, you get -1 out of it after you do this, right? So this means a bit by bit multiplications, and you add them together. So you divide them by 8, right? So you can see the receiver extract the original information successfully. When you send out the -1, 1, you get extract -1 and 1 again by the receiver, right? By using the decoding, by using the same chipping sequence. So that's the deal of CDMA. So if you have multiple users, you are fine. Everybody can do the same. So these slides show you a little bit complicated example. The only differences between this slide and the previous slides is that previous slides we only have one sender, but this one we have two senders. Two senders mean that each of the senders you may have different chipping sequence. Okay, so right here in this graph you can see this is the chipping sequences for sender 1, right? It is 1, 1, 1, -1, 1, -1, 1, -1, -1. For the sender 2, you can see it's quite different chipping sequence, and they are all solved now. Okay, it's totally different chipping sequence we use. So, so what happens right here is you do the same things for the senders, just like the previous example. You do bit by bit multiplications, right? Multiplications and send out. Okay, and excuse me, sender 2 do the same thing. You use its own chipping sequence. And because this is a common channel, they are sharing the channel, right? So their signals is going to be added together, bit by bit, synchronized. So from the channels, the waveforms you will see is the added message waveform, like this. Okay, this is 0, -2, 0, 2, 0, 0, 2, 2, 2, 0, 2, 0, 2, right? So that's the waveform. After the information of these two senders are mixed with each other, you cannot tell what they are at all, right? For example, if you have a hacker, they don't know what they are. So you may be wondering why and how the senders we would be able to extract the information out of this added information. So actually there's no difference than the previous example. So supposedly we are receiver 1. Okay, we got the combined waveform from the channel and we want to extract useful information for receiver. So only receiver 1 is able to extract useful information -1 and 1 out of the channel. That's the goal. By using the chipping sequence, the same chipping sequence is shared with the sender, like a secret key. Okay? But for whoever don't have this key or this chipping sequence, they are not able to get steal the information that does not belong to them. Okay? So for receiver 1, for example, the combined waveform is right here. For receiver 1, you use the same chipping sequence right here to process it. So again, no differences than the previous example. you do bit by bit product and add them together. Okay, for each of the slot, you do bit by bit product, add them together, and divide by 8. Illicit spreading factor is 8, right? M is 8. By doing this, you are able to recover, extract the first data bit slot. Similarly, for the slots, you do similar things. Run these things, bit by bit product, add them together, divided by 8. All right. So you can see, if you try this manually, you will be able to see the result is exactly -1. That's the exact same information you send out in the sender 1, right? Which is slot 1 you send -1, slot 0 you send positive 1. So you are able to recover the information. So similarly, for receiver 2 or all the other receivers that share the channel, they are able to recover their own information out of the combined waveform or some channel data. So this is a very useful technology, isn't it? Right? So try to understand it, do a little bit of exercise by your own hand to understand the corrector. And also I give you simple examples of this. So supposedly you have 2 CDMA senders use the code of this and this. So they are different chipping sequence, right? So pretend to suppose the first sender send out bit 1, the second send out bit -1. Ask you to see what is the combined signal waveform by the receiver. I want you to draw the waveform. So basically, what I ask you to do is the first step. All right, how to calculate the combined waveform. And in this exercises, we only have 1 bit of data. We don't have 2 slots. We have only 1 slot. Right? In this one, we have 2 slots. So this exercise actually is simpler compared with the previous one. I don't ask you to do excuse me, the extraction of the information. So it should be easy. Get some exercise, okay? Because in the exams you may see some similar problem, right? So the next thing is about L2.11 Wi-Fi or wireless LAN technologies. So L2.11 Wi-Fi actually, as I showed you, there are different sub-protocol. Okay, and in L2.11 we use 2.4 gigahertz spectrums, and the transmission speed is from 1 to 2 megabits per second. It's quite slow in the old days. Okay, the original Wi-Fi protocols. Now we don't use this; it's too slow. Instead, widely used Wi-Fi protocol suite is 11B, 11A, 11G, 11N. Okay, 11B is use the same 2.4 gigahertz spectrum. It can achieve 11 megabits per second throughput. It uses DSSS, which is direct sequence spread spectrums, which we discussed previously, right? In the last couple of lectures, in the last couple of slides. 11N uses 5.8G, so its speed is faster, right? 54 megabits per second. 11G is used 2.4, okay, still, and 54 megabits. 11N you can do MIMO, which is you use multiple input and multiple output. You use multiple antennas to do transmitting and receiving, and you can use either 2.4 gigahertz or 5.8 gigahertz, and the transmission speed can be up to 200 megabits per second. So these are all different physical layer specifications, what kind of frequency you are using for modulation. But For the MAC layer, they are all the same for all the Wi-Fi. Okay, they just have different protocols suited to accommodate different physical layer parameters. For MAC layer, they all have to use CSMACA. So it's not CSMACD. In CSMACD, it is collision detection, right? It's used in Ethernet or L2.3. Wide Ethernet, right? For multiple access collision detections. When you see some collisions, you just avoid. Right? But for wireless, it's different. The CDMA-CD does not work because of the hidden node problems and exposed node problems, which cause the fundamental differences between the wide media and wireless media. So we have to do something different. We will explain more why. Okay. And also for these Wi-Fi protocols, all have base station or infrastructure mode or ad hoc network mode. You can either work notebook directory or Wi-Fi direct, or you can all go through a central base station. And it supports multiple priorities. It supports time critical and data traffic. And if you are idle, you are allowed to sleep, save some energy. Or this is called doze off, right? Power management to save power. So in L2.11 architecture, this is the first straightforward architecture, or L2.11 local area network architecture. So in these architectures, a hub or switch or routers connected to multiple BSS. BSS is the fundamental unit of L2.11 architecture. So it's called Basic Service Set. Okay. So basically, one router can be used to connect to multiple BSS. So each of the BSS actually is a cell tower. You have an access point, right? You have an access point and multiple mobile devices connect to this access point. So this comprises of a single basic service unit set, BSS. Okay. So if you have a AP, then if you work in infrastructure mode, then each such set is BSS. But if you are working in an ad hoc mode, that each of the BSS only have hosts that are connected with each other, there will be no AP, right? So in L2.11 channel, what we do is, for example, 11B, so we divide these spectrums into 11 channels at different frequencies. So each frequency is with some, each band is, or channel is with some fixed frequencies. And you can choose which frequency. And if you have so the users will use these frequencies. So there's a chance that multiple Wi-Fi signals in specific locations may using the same frequency. And it will be causing interferences. Okay, so that's why in some very crowded areas, the Wi-Fi network can be very slow. It's not in a lot of cases, such places the slow Wi-Fi connections can be caused by interferences. Okay, and also for L2.11, before you are able to transmit anything, the hosts, if they are working in infrastructure mode, they have to associate with AP first. So that's something you are very familiar with. So when you move to a new location, you look for Wi-Fi. So what you see is that you always listen for some beacon frames from the nearby or close by access point. They will tell you the basic informations. Excuse me. Like SSID, right? The name and MAC address. Okay. Then you may decide to connect it to one of them you want to associate with. If there are signal, if there are password set, if it is encrypted, then you would have to input the password, right, and perform authentications. If it is free, then you do not have to do this. You just associate with AP. Then you can get connected. But if it is secured, then you just input your passcode and you get connection. And if you pass the authentications, then typically what will happen is the DHCP server of that Wi-Fi network will announce the IP addresses you can use and send it to you. And you will get the router IP address, you will get the DNS address, so on and so forth, by using typical DHCP process. Okay? So for this scanning process, when you move into a new BSS, there are two kinds of scanning process. So the first one is called passive scanning, and the second one is called active scanning. So passive scanning is very simple. So it means that the beacon frames is sent out by AP first. You're just listening. You're just listening to all kinds of beacon information from other people. Okay? And you decide which one to associate with. Okay, you select the ones. For example, in this case, you select the AB2. Then you respond with association response. Okay, so after several further steps, you are associated to this AP. So this is a passive scanning, which means you're just listening passively for the beacons. Or you can do a little bit differently. You can do active scanning, which means whenever you move to a new location, you just actively ask for the possible AP that can work for you, or you can associate with. Okay? For example, in these cases, what happens for active scanning is you send out probe request frame and broadcast it to all the AP around you. And the response frames will be sent out to you by both AP. And then you decide which one to select from. Okay? So if you decide to associate with this guy, you finish the process 3-4, right? And associate with this AP. So you can see the difference between passive scanning and active scanning. The only differences is that this one you're just listening to the beacons, right? You don't actively ask around, but this one you actively ask around. Okay, that's the only difference. So as I mentioned, in Wi-Fi or L2.11s, you have to do something differently for collisions or competitions among different hosts, right? In wide line Ethernet, when you send out something, all the neighbor stations know immediately. But this is not the case for wireless, right? For wireless, because of the hidden node problem, exposed node problems will cause issues. So we need to do something differently for this competition. Okay, so in L2.11 in Wi-Fi, we do similarly. We do similarly in the sense that we do carrier sensing. Okay, we sense before transmitting. If somebody is transmitting, we don't interrupt other people. That's the bottom line. But the collision detections which works for Ethernet does not work for wireless Wi-Fi. There are two reasons. Okay, the first reason is very difficult to receive when transmitting due to weak receive signals or fading. So, as you know, that for wireless, it's very costly to detect collisions because it's very difficult to to receive while transmitting. Okay, in wired line it's easy, but in wireless, it could be very, very costly if you want to do this because of the fading. Right, the signal is weak. So that's why we do not do collision detection, because some node is far, some node is close, these have different signals, and how do you decide its collisions? It could be hard. And in the cases of hidden node or fading, which both cases cause the hidden node problem, then you cannot sense all collisions in any cases. So we need to do it a little bit differently. So the different protocols we use to avoid collisions is called CSMA-CA. All right, it's not CD. CD is collision detection. CA is collision avoidance. That's specifically useful for wireless. Okay. And we will discuss how that things work. So basic ideas is when we do Ethernet collision detection, what we do is when you send some things, everybody see, but in Wi-Fi you cannot assume this. So to resolve any collisions, what we do is we use CSMA-CA. The fundamental idea is you listen before you talk. If the medium is busy, you back off, right? And you try to avoid collisions of long frames, which means that you are still it's still possible you may collide for short frames, but for long frame we don't want collisions, right? So what happens? We in CSMA-CA we send out a short reservation message, or RTS. We want the decision to be made by the receiver, right? So in hidden node problem, when A and C want to send it to B, they just assume B has the same situation as A and C, but as a matter of fact, it is not, right? We need we need the receiver B to make the decisions, who to take the message, whose transmission to pick up, right? So that can be done by using CSMA-CA, which essentially is a reservation mechanism. It's kind of reservations mechanism allowing the receiver to make decisions. So, for example, RTS is kind of requested to send its reservation message to send it to the receiver. Okay. It contains the destination address, duration of the message, and basically telling everybody to back off for that duration. So whenever the destination, the receiver, got the message, he will make the decision. He will see, oh, if multiple guys want to send to me simultaneously, I will need to see who got to send me the request first. He will get this first, right? So then he will send clear to send, which means that, okay, I got your reservation request. I will reserve this for you, and all the other stations around me will defer, will wait. All right, they cannot detect collisions, but you essentially request each packet is acknowledged because you are not able to detect collisions. So it's kind of in wireless we have to ask each packet to be acknowledged. Okay, so we will continue our discussion in the next lecture. Okay, thank you so much. See you next time.